Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is lecture number 24 and week 12. We will continue capacitors from the last class, and this is chapter 10 of the book Introductory Circuit Analysis. These are the today's lesson contents: type of capacitors, capacitors in series and parallel. So, like resistors, all capacitor can have fixed or variable values. So कैपेसिटर जो है वो फिक्स वैल्यू के भी होते हैं और वेरिएबल भी होते हैं, जिस तरह से रजिस्टर जो है वो फिक्स रजिस्टर्स भी होते हैं और वेरिएबल रजिस्टर जिनको हम पोटेंशियोमीटर कहते हैं वो भी अवेलेबल है. सो दिस इज सिंबल ऑफ फिक्स, this symbol of variable resistor. The curved line represents the plate that is usually connected to the point of door potential. So ये जो टर्मिनल होता है कर्व जो सिंबल है इसको आप नेगेटिव बैटरी टर्मिनल के साथ यूजुअली कनेक्ट करते हैं, और ये जो टर्मिनल होता है फ्लैट इसको आप पॉजिटिव टर्मिनल के साथ कनेक्ट करते हैं. So associated specifications with the capacitors are the working voltage and the surge voltage. So other than the value of the capacitor, the capacitor usually specifies the associated voltage, that is its working voltage, and the surge voltage. What is the working voltage? Working voltage is the voltage that can be applied across the capacitor for long periods of time without breakdown. So for example, एक मेरे पास अगर capacitor 50 वोल्ट का है तो उसके ऊपर मैं 50 वोल्ट या इससे कम वोल्टेज एक किसी भी लॉन्ग पीरियड ऑफ टाइम के लिए मैं उसके ऊपर अप्लाई कर सकता हूँ, और इससे जो आपका कैपेसिटर है वो डैमेज नहीं होगा. However, the surge voltage is the maximum DC voltage that can be applied for a short period of time. The surge voltage is the voltage that only happens for only short period of time, and then will vanish, and that voltage is only return for a very short period of time, and it is the maximum DC voltage that can be applied across the capacitor. Many types of fixed capacitors are available today. Some of the most common capacitors are made with these materials: mica, ceramic, electrolytic, tantalum, and polyester film capacitors. So these type of capacitors that we will see in the next slides are available in the market, and these are the materials by which these capacitors are formed. So capacitor have two plates. One is positive and the other is negative, and the third thing that in a capacitor is a dielectric material. So based on the material used for plates and the dielectric, these capacitors are categorized and are available in the market, and there is a variety of capacitors that you will found which offer different values, which are used in many applications. So this is a mica type capacitor with the mica foils and mica insulator sheets for separation. The typical flat mica capacitor consists basically of mica sheets separated by sheets of metal foils. So this is mica used as an insulator, and these are the metal foils used for the capacitor plates, positive and negative. So these ones are for example positive. These are the positive plates, and these two are for example the negative plate of the capacitor. So physically it appears in this form. In this form, these two tiny flat capacitors. These are the mica capacitors. These are typically the electrolytic capacitors. These are the few important details about the mica capacitor. The total area is the area of one sheet times the number of dielectric sheets. The entire system is encased in a plastic insulating material, as shown in the previous slide, and the mica capacitor exhibits excellent characteristic under stress of temperature variations applications. This is a ceramic type capacitor in which ceramic materials are used. Ceramic is a kind of insulator which is used between the conducting plates. Then you have monolithic capacitors, which are used in small integrated circuits. Their size is pretty small, and they are usually surface mount. There are also has been increasing use of microstrip circuitry, such as shown in this figure. Then we have electrolytic capacitors. They are designed primarily for use in DC networks because of good insulating characteristics, high leakage current. This is the disadvantage of the electrolytic capacitors, and in one direction they have good insulating characteristics in one direction, but take on the characteristic of a conductor in the other direction. So these are the electrolytic capacitors. The overall area of this capacitor is large, and due to this and due to the use of an oxide as the dielectric, the distance between the plates is extremely small. So oxide is used as dielectric in this type of capacitors. The negative terminal of the electrolytic capacitor is usually the one with no visible indication on the casing. The overall area of this capacitor is large, and due to the use of an oxide as the dielectric, the distance between the plates is extremely small. So the oxide is used as dielectric in these type of capacitors. The negative terminal of the electrolytic capacitor is usually the one with no visible indication on the casing. However, the positive is indicated by such designs as these symbols, which are used to indicate the positive terminal on the capacitor. So due to the polarity requirement, the symbol of electrolytic capacitor will normally appear as this, with this positive terminal, and this one is negative terminal. So next is tantalum capacitor. This capacitor looks like next is a tantalum capacitor. They are fundamentally two types of tantalum capacitors, the solid and the wet slug. In each case, tantalum powder of high purity is pressed into a rectangular or cylindrical shape, as shown in this figure. Then we have polyester type capacitors, in which these are the polyester films or plastic films, which which are used to form as an insulator between these metal foils. This is a polyester type capacitor. If large values are printed, or else color coding is used on smaller devices, so their values are printed on the body of the capacitor. Also a band, usually black, is sometimes printed near the lead that is connected to the outer metal foil. The lead nearest this band should always be connected to the point of lower potential. So usually a band is also being indicated here to indicate the negative terminal of the capacitor. Its leakage resistance is of the order of 100 megohm. The axial lead variety is available in this range with working voltage of this much, and the radial variety has these values and working voltage of 1000 volts. These are the variable type of capacitors whose capacitance values can be varied using the shaft arm. Sliding this arm will basically change the overlapping area of these plates, and the value of the capacitors would be changed. And in this type of variable capacitors, a screw knob is provided to change the value of these capacitors. Next is the measurement of a capacitor. So to measure the value of a capacitor, meter, which is called the digital capacitance meter, can be used to measure these values if they are connected in proper polarity. An ohm meter, when connected in proper polarity with fully discharged capacitor, can indicate deterioration in capacitors. So ohm meter can be used to measure a capacitor to be connected across a capacitor, but the ohm meter will not give the value of the capacitance, but it will indicate the status of the capacitor, whether it is a good or a bad. That is there any damage that occurs into the dielectric of that capacitor. So deterioration in the dielectric can be indicated by the ohm meter if applied properly. So a low resistance reading 0 to a few hundred ohms normally indicate a defective capacitor. So if a meter indicates a low resistance, then it means that the dielectric is broken or damaged. And if the reading is very high in the mega ohms range, then this capacitor is in the good form. These are the standard values of the capacitors which are available in the market, from the 0.1 microfarad to 4.7 microfarad or even higher. So these are the few types of capacitors and their marking schemes. These are the parameters or specifications which are indicated on the capacitor. First one is the value that is indicated on capacitor, and the second one is the typical voltage range, and these capacitors have some tolerance plus minus 20%, that their value is can be off from its nameplate value of that is indicated on its body. So these are the ceramic capacitors, tantalum capacitors, and these are the surface mount type, and these are silver mica and mylar paper capacitor. These are the variable capacitors, which are also called trimmer. Next is we can connect capacitors in series and parallel to make the capacitance which are not commercially available. So increasing level of capacitance can be obtained by placing capacitors in series, while decreasing levels can be obtained by placing capacitors in increasing levels of capacitance can be obtained by placing capacitors in parallel, while decreasing level can be obtained by placing capacitors in series. We will see how we when connect capacitors in series, their overall value will when we connect the capacitors in series, the overall value will decrease, while when they are connected in parallel, the overall value will increase. Now for a given circuit, applying KVL for this circuit, then we can see that the applied voltage would be equal to sum of voltage drops across each capacitor. So E is equal to V1 plus V2 plus V3, but we know that for a capacitor Q is equal to CV and V is equal to Q by C. Thus we can have from here Q is the total capacitance and E is the applied voltage. Sorry, Q is the total charge and E is the applied voltage, and T would be the total capacitance of the series capacitors. So QT by CT would be equal to Q1 by C1, Q1 by C1, this is capacitor C1, Q2 by C2, V3 would be equal to Q3 by C3, so V3 would be equal to Q3 by C3. So we can further proceed with this equation. As for capacitors in series, the charge is the same on each capacitor. So when the capacitors are connected in series, then every capacitor would have the same charge, like when resistors are in series, then all resistors have the same current. So total charge would be equal to charge Q1 and it would be equal to Q2 and Q3. So all the charges would be equal. So Qt would be equal to Q1 and Q2 Q3. Then thus by dividing by Q we get if all these charges are equal, then we can take common from this equation, and then they would be cancelled, and we will get from this equation 1 over Ct equal to 1 over C1 plus 1 over C2 plus 1 over C3. And so total capacitance of the series circuit would be the reciprocal sum of the reciprocal total capacitor would be equal to reciprocal sum of all the capacitances. The voltage across each capacitor of figure can be found by first recognizing that all the charges are equal, and then we can apply this equation to find out the voltage. That would be equal to Q by C, and for any capacitor Q 1 by C1, if we know the value of charge on of any capacitor, we can find out corresponding voltage. Or we can write it as for any capacitor X, we can write it as Qt is equal to C into Ct into E, which is equal to C1 into V1, and C1 this would also be equal to C2 V2 and C3 V3. So from which we can find out voltage drop across any capacitor. That would be equal to Ct into E divided by C1. Now when capacitors are connected in parallel, then as shown in this figure, then we can see that the voltage across each capacitor would be equal, and it would be equal to E, and how much the charge that would be established on each capacitor, that would be equal to the total charge would be equal to the sum of the individual charges. So Qt would be equal to Q1 plus Q2 plus Q3. However, Q is equal to CV, so we can write it as Ct into E, that would be equal to C1 into V1 plus C2 V2 plus C3 V3. And but for parallel, we know that the voltages across each component would be equal to the applied voltage. So these all voltages would be equal, and they can be taken out and cancelled on either side. So total capacitors would be equal to sum of all the capacitances. These are just the series sum of this is like the series sum of all the resistors, but for capacitors, when capacitors are in parallel, they would simply be added. Next is the example in which we are asked to determine the charge on each plate and voltage across capacitor C1, or voltage across each capacitor. So we can find out the total capacitance, and total capacitance of series capacitors is determined by this formula, and by plugging the values, CT would become out to be 8 microfarad. And for series capacitors, the charge on each capacitor would be equal, and if we know the voltage and the total capacitance, we can find out the total charge by using this equation, and it turns out to be 480 microcoulomb. So charge on each capacitor would also be 480 microcoulomb. So from here we can find out voltage V1, voltage across capacitor C1, that is V1, and it would be equal to Q by C, Q1 by C1, and Q1 is equal to 480 micro, and C1 is the capacitance 200 microfarad. It would be equal to 2.4 volts. Next is the example in which there is parallel combination of these capacitors, and you are asked to find the total charge QT. So for that we can find out the total capacitance first of all. So total capacitance would be the sum of all these capacitors, that is 800 plus 60 plus 1200 microfarad. So adding all these, we will get 2060 microfarad. And if we know the total capacitance, we can find out the total charge by using the formula as by using the formula as QT is equal to E into CT. Or we can find out Q1, Q2 and Q3 and then add all these to find out the total charge. So Q1 would be equal to C1 into E. Similarly Q2 is equal to C2 into E, and Q3 is equal to C3 into E, because for all the capacitors, voltage across every capacitor is applied voltage E, because they are in parallel. So Q1 would be C1 is 800 micro and E is 48 volts. So we will get this much capacitance, and for Q2 and Q3. Then adding all these charges, we can find out the total charge. Next is the example in which you are asked to find the voltage across and charge on each capacitor. So what is the voltage across each capacitor, and what would be the charge on each capacitor? So how can we find out the charge? That we will show in this example. So first of all, we can find the total capacitance of the circuit by knowing that these two capacitors are in parallel, so they can simply be added. So adding these two would turn out to be 6 microfarad. So this is 6 microfarad. Then this 6 microfarad capacitor would sit in series with this 3 microfarad, so they would be in series. So when they are in series, then they would simply be added. These are the series combination. So this is 3 micro and this is 6 micro. So when you solve these two in series, so formula would be the formula for parallel computation. So this is the formula that can be used to find out the total capacitance, that would be 2 microfarad. So once we have the total capacitance and total applied voltage, we can find out total charge by this relationship. Then we have to reverse back our analysis, and we shift from this circuit to back to the original circuit by knowing that the total charge on this capacitance and this capacitance, they would be equal because the both are in series. When the capacitors are in series, then charge would be equal on each capacitor. So Q2 would be equal to Q1, Qt would be equal to Q1 would be equal to Qt dash. So Q1 and Qt dash would be equal. So the charge that enters here is Qt dash, that would be split into these two capacitances. From this information, that is from charge Q1, which is 240 micro, we can find out voltage across V1 by using this relationship. V1 is equal to Q1 by C1, Q is equal to CV, and V1 is equal to Q by C. The Q1 is we have just computed, and C1 is the capacitance given, so it would be 80 volts. And also for Qt dash, we can use this value to find out the voltage Vt dash that appears across these two capacitors, which would be equal to Vt dash would be equal to Qt dash over Ct's, which is equal to 40 volts. So voltage drop across these two capacitors would be 40 volts, and voltage across Q1 is 80 volts out of 120 volts. So for 120 volts, 80 would be drop across this, 40 would drop across these equivalent capacitors are capacitances C2 and C3. Revert back to original part of the circuit. Now voltage across parallel part of the circuit is Vt dash, which is just computed as 40 volts, and we can use this voltage to find out the charge on each capacitor. So these are the results. Next example is find the voltage across and charge on capacitor C1. So what is the voltage across this capacitor for a 24 volts applied, and these are the two resistors. We are asked to find out the voltage across this capacitor C1, and what is the charge Q1 that is accomplished across this capacitor. So for the solution, the capacitor is effectively an open circuit for DC after charging up to its final value. So we are asked we have a condition that to find the voltage across and charge on capacitor C1 after it has charged up to its final value. So when capacitor is fully charged, then after fully charging a capacitor, then there would not be any current that would flow in the capacitor to further charge the capacitor. So the current would be zero, and this capacitor would behave like an open circuit in which no current would flow, as in open circuit current is zero. So the capacitor is effectively an open circuit for DC after charging up to its final value. Now with this open circuit, the voltage across these open terminals would be the voltage across resistor of value 8 ohms, which we can find by using voltage divider formula with the applied voltage of 24 volts. So 24 volts into 8 divided by 4 plus 8, it would be equal to the voltage across resistor 8 ohm, which would also be equal to Vc. So Vc would be equal to by computing these values, we will get 16 volts across this capacitor. Once we know the voltage across the capacitance, we can use these values to find out the charge on capacitance by using this equation. So it would be 320 microfarad. So this is the summary, the type of the capacitors and the capacitors in series and parallel. That's it for today. Thank you. Allah Hafiz.